In this problem, we are given the description of a sphere that is in free fall. We are told that the height through which the sphere is dropped, so the height of the tower, which I'm labeling as delta y, is equal to 145 meters. And we're also told that the sphere itself has a diameter of 1 meter. Now that's all the information we're given for part A of the problem, which asks for how long the sphere is in free fall, so how much time it takes for the sphere to fall 145 meters. Well, if we assume that the acceleration is constant, then we can apply our kinematics equations for constant acceleration. And I've taken the time to write out those formulas on the side. Since we're dealing with a situation where the object is in free fall, the acceleration is just the gravitation acceleration, so the acceleration due to gravity of 9.8 meters per second squared. So to find the time it takes for the sphere to hit the bottom, we're going to need to pick the right equation for us to use. Recall that for these types of problems, the best equation to use is going to be the one that has all the variables we're given, the variables we know, and the variable we are trying to find. And the one that seems to fit the bill the best in this case is the second equation, because we know delta y, we know the acceleration, and we're trying to find time. And since the object is dropped from rest, we can assume that the initial speed is 0. So delta y equals v naught multiplied by t, and since the initial speed is 0, v naught is 0, and this entire term disappears, plus 1/2 multiplied by the acceleration, which is g, multiplied by the square of the time. So what we want to do is algebraically rewrite this equation to solve for t. So multiplying both sides of the equation by 2 and dividing both sides by g to get it on its own. T squared is equal to 2 multiplied by delta y over g. And then taking the square root of both sides to solve for t, we can see that t is equal to the square root of 2 delta y over g. So to solve part A of the problem, we're just going to need to plug in the values we're given. So 2 multiplied by delta y, which is 145 meters, and we divide by the gravitational acceleration of 9.8 meters per second squared. Put that into a calculator, and we find a time of 5.44 seconds. And so that is our answer to part A. Part B of the problem asks us to find the speed of the sphere just as it hits the bottom. So once again, going back to our equations, now we want to pick the equation that includes a final speed, the v variable. So we could use either the first or third equation, but now that we have the time, we can really use either of them. I'm going to use the first equation just because I think that's a little more straightforward. So v equals v naught plus acceleration multiplied by time. Once again, v naught is just 0, plus the acceleration, which is 9.8 meters per second, multiplied by the time, which we just found to be 5.44 seconds. Put that into a calculator, and we find a final speed of 53.3 meters per second. Now the final part of the problem, part C, describes what happens to the sphere just after it hits the bottom. It is caught by some kind of catching device that moves the ball through some distance as it is decelerated to a final speed of 0. We're asked to find what that distance is if the acceleration of that deceleration is 25 g's. So now we're going to have to define entirely new variables for this section of the motion. So I'm going to say acceleration sub 2 is the 25g acceleration that is given in the problem. Our new initial velocity for this part is going to be the final velocity for the previous part of the motion. So v naught 2 is 53.3 meters per second. And the new final velocity, since it's being decelerated to rest, is 0 meters per second. And we're being asked to find the distance, so delta y sub 2, you could say. Now going back to our list of equations, we have the initial and final speeds, we have the acceleration, and we're looking for the displacement. So it seems now that the best equation to use for this part of the problem is the third equation, which has all the variables we're given for this part, and it has the variable we're trying to find, the delta y. So our starting equation for this part is v sub 2 squared equals v naught 2 squared plus 2 a sub 2 delta y sub 2. And we're looking to solve for delta y sub 2, so we'll subtract from both sides of the equation v naught sub 2 squared, and then divide both sides of the equation by 2a2. So we find that delta y sub 2 is equal to v sub 2 squared, v naught sub 2 squared, all divided by 2a sub 2. So of course the final speed is 0, and 0 squared is just 0, minus the square of the initial speed, which is 53.3 meters per second. Don't forget to square it. Then we divide by 2 times the acceleration, which is 25g, so that's 2 times 25 times 9.8. And if we put this into a calculator, then we find a distance traveled of negative 5.8 meters. What we just found is negative because the sphere is traveling downwards in a negative direction, but since the problem's only asking for a distance as a scalar, we can ignore the negative sign in our final answer and just write 5.80 meters. And that is it for this problem. I hope this video helped you out. If it did, please consider subscribing, as that'll help me out in making more videos just like this. If you have a request or a question, leave a comment down below, and I'll do my best to help you out as best as I can. That's all for now, and I hope you all have a lovely day. Bye-bye.